Alright, welcome to our atomic structure notes. We are going to be covering information today on sections 4.2 and 4.3 of our textbook. Our goals today are to describe the basic structure of an atom, be able to read the periodic table, explain why isotopes are important, and model ionic and covalent bonds. Okay, let's start with the structure of an atom. Okay, so this is our very simple model of an atom. Okay, in a lot of ways this is inaccurate. The primary one being that electrons don't really orbit the nucleus. But this is a good model for us to learn how atoms bond, so we're going to stick with it for today. Alright, so we have the nucleus. Inside of the nucleus we have our protons and our neutrons. And then flying around in like this electron cloud thing, we have our electrons, which are the tiny dots. Okay? Most of our mass is in the nucleus because the electrons don't really have much mass at all. You're also going to see me write these abbreviations for protons, neutrons, and electrons a lot. I like them because they help you remember what charges they each have as well. Alright. Even though electrons are not actually in these shells, we still write them this way, and we consider there to be 4 shells, K, L, M, and N. K can hold 2 electrons, L can hold 8 electrons, and although M and N can hold a lot of electrons, for our purposes they're only going to hold 8 each. Alright, here's our periodic table. Now, a word of warning, different periodic tables are going to look different. Some of them may have more information than this one, some of them may have less information than this one, and they may not be written in exactly the same way. So you really have to kind of pay attention depending on the periodic table you're looking at. This periodic table has the atomic number in one corner and the atomic weight or mass in the other corner. In the middle you have the chemical symbol, and then at the bottom you have the name of the chemical. This is basically all the information that we need to know for biology. Right? The atomic number is the number of protons. That's also an identification number. You will notice that there is no element on this table that has the same number of protons. Okay, that is different for every single element. Right? The atomic weight or mass is the number of protons and neutrons. It is not a whole number. Okay, that's one of the best ways to tell the difference. It is not a whole number because it's actually an average, and I'm going to explain that in a second. However, when you're doing calculations for our purposes, you can round either up or down depending on what the number is. And you would need to do that if you were trying to find the number of neutrons. Okay, in order to find the number of neutrons, and I have it written down here, you have to take the atomic mass and subtract the atomic number. There we go. Each column is called a group, and all the elements in a column have characteristics in common. The characteristic that we really care about in biology is how many electrons they have in their outer shell. And I've written that on top of each of the columns. Okay, so the 1 electron, 2 electron. Okay, that's the amount of electrons that are in the outer shell, or they're also called valence electrons. You'll notice I didn't write any here, and that's okay because we don't really have to worry about these guys, and they follow their own rules anyway, so we're just going to leave them be. If for some reason one of them comes up, I would give you that information. The other thing that I wrote up here is I wrote the charge that these elements in each group would have when they were an ion, okay, whether it's a positive or negative charge. Okay. The only exception is the noble gases because they very rarely make chemical compounds. You are responsible for knowing the first 20 elements, and I mean that in reference to their atomic number, so you need to know hydrogen, helium, across this row, across this whole row, all the way up to calcium. Okay, those ones you should know the name and the symbol for each. All right, you don't have to memorize how many electrons in the outer shell or what their charges are, but you do need to know their name and their symbol. Okay, so I remember I said that the atomic mass is an average. The reason for that is because there are different versions of atoms or of elements. They all have the same number of protons, but they have different numbers of neutrons. Okay, so here are two examples. We have carbon-12 and carbon-14. Carbon-12 has 6 neutrons. So its atomic mass is 12, because that's 6 plus 6 is 12. Carbon-14 still has 6 protons because it has to, but it has 8 neutrons. So its atomic mass is 14. There's also another one in here that's carbon-13, but I took it out. I didn't really care about it. Carbon-12 is a lot more common, and that's why when you look at the atomic mass of carbon, it's like 12.001 or something like that. There's only a small percentage that's carbon-14. Carbon-14 is not stable. That means that the way that it is, it can't hold itself together, and it has to do with the extra neutrons. When an isotope is unstable, it's called radioactive. And what radioactive means is that it's releasing little bits and pieces of energy. And eventually it will break down into a new element. The energy that it releases is called radiation. And although this can be dangerous, there are a number of uses in science. Okay. For example, carbon-14 is used in what's called carbon dating. So when they come across really old things like fossils or like archaeological digs, they can use carbon-14 to find out how old it is, because they know the rate that it breaks down or decays. We also use radioactive elements for energy, and they're also used in medicine. So they have a lot of positive uses in science. Okay, this is kind of the big deal here, is our bonding. How do we make chemical compounds? Okay, so we're going to run through 2 examples because I think that's the easiest way to do it. All right, so we have a sodium atom. Okay, sodium on its own is a metal. It's on the left-hand side of the periodic table. And we have a chlorine atom. Chlorine is a gas. It's a poisonous gas. And because it's a nonmetal, it's on the right hand of the periodic table. Now, when these two chemically combine, they become a common household substance, table salt. That's called sodium chloride. That's table salt, which we eat and love on a regular basis. So how does this happen? Well, a sodium atom has 11 protons. Okay, I know that because if I looked it up on the periodic table, it would have an atomic number of 11. That means it also has 11 electrons, which gives it, as a neutral atom, which is the way it's written on the periodic table, it has a charge of 0. The chlorine atom has an atomic number of 17, so that means it has 17 protons, and therefore it has 17 electrons rather, and its charge is 0. Now here's the thing about atoms. They would prefer that their outermost energy shell be completely filled with electrons. But that's not what naturally happens in a neutral atom. So that's what is like the impetus towards atoms making bonds with other atoms, because they're trying to fill up their outer energy shell. Alright, so let's look at sodium. Sodium has 2 electrons in the first shell, has 8 electrons in the second shell, that's 10, and then 1 electron in the third shell. Okay. If you need reminders about how many electrons fit in each shell, look back at that. It was like the first real slide, okay, that gives you those numbers. Okay, chlorine puts 2 on the inside, 8 on the second, and that leaves 7 in its outer shell. Okay, so we would say that sodium has 1 valence electron, and chlorine has 7 valence electrons. Now, it happens to be that in an ionic bond, the metal is going to give electrons and the nonmetal is going to accept the electrons. Here's why. In order for sodium to fill this outer shell, it would have to find 7 other electrons to make a total of 8. Or it can just give away this 1 electron, and then it's going to be left with the second shell, which is already full. Okay? And if you look at chlorine, it either has to get rid of 7 electrons, or it just has to find 1 electron, and then it will fill its third shell. So since it's easier for sodium to give away 1 electron and for chlorine to find 1 electron, that's what happens. Okay, so sodium gives its electron to chlorine. Okay, now sodium has given it away. It doesn't have it anymore. So it still has 11 protons, but now it only has 10 electrons. So it has 1 extra positive, and we call that its charge. Okay, so we say it has a +1 charge. Chloride now has 1 extra electron. So although it still has 17 protons, now it has 18 electrons or negatives, so it has a -1 charge because it's got an extra negative. Notice, however, that if you take the charges and add them together, they come out to 0. So the compound together has an overall charge of 0, even though the ion has a positive and a negative charge. Okay, now if every time we wanted to do this, we had to draw out these atoms, it would be very time consuming. So what we do instead is we write what's called a Lewis dot structure. And in a Lewis dot structure, you just write the valence electrons, or the electrons that are in the outer shell. Okay, the way that you do this is you pretend that there's a box around the symbol. Okay, there's an imaginary box. And each side of the box can hold 2 electrons. Since there's 4 sides, you end up with 8 electrons. Okay, sodium only has 1 electron, so that one is easy. We're going to put him there. That's his 1 electron in his outer shell, his valence electron. Chlorine has 7 electrons. So we start, and you go around and fill them in. All right, so there's 1, 2, 3, 4, 5, 6, 7. Now sodium is going to give its electron to chlorine. The way we show that is by drawing an arrow. Oops. Okay, that arrow means that sodium is giving its electron to chlorine. All right, and then we finish it up by putting a +1 by sodium, because that's its charge, and a -1 by chlorine, because that's its charge. Covalent bonds, on the other hand, share electrons. So one doesn't give an electron to the other, they both share them at the same time, which is very nice. Sometimes they make the joke that covalent bonds passed kindergarten with flying colors. All right, so here's two examples. Here are two hydrogen atoms. Okay, now hydrogen only needs 2 electrons to fill its outer shell. It does not like having just 1 electron. So those two hydrogens are going to share. They're each going to contribute an electron, and we note that they're being shared by circling the paired electrons. Okay, so in an ionic bond we drew an arrow to show it moving. Here we're drawing a circle to say that it's being shared. Okay, here's oxygen. Oxygen has 6 electrons in its outer shell. It has 2 unpaired electrons. Okay, so these need to find an electron to share with. We can grab 1 hydrogen and add it on, but we're still going to have an unpaired electron. So we need another hydrogen. Okay, and that's what happens. And this is H2O, water. Okay, so each hydrogen shares 1 electron with the oxygen. So oxygen has 8, hydrogen has 2. Okay, and they're sharing these electrons. I should also note, and this is important, that this happens between 2 nonmetals, right? So hydrogen and oxygen are both gases. Oh, which reminds me of something else that I should tell you. I forgot to do this. I did mention this just now, but these are all metals except for hydrogen. Hydrogen is not a metal. However, everything else fits in with the first group. Okay, and these are all nonmetals. All right. These up here are, like I said, the electrons that are in the outer shell. So remember, I just said that oxygen has 6 electrons in its outer shell. Okay, and if you didn't believe me, you can write out the energy shells and you'll see that that's true. Okay. If we're not writing Lewis dot structures, the 2 other ways that we can draw molecules are chemical formulas or structural formulas. Sometimes in the book you'll see space-filling models, which are good when you're trying to see the different sizes of the atoms, but aren't really very useful for us in biology. So the ones that you're going to see the most in here are structural formulas and chemical formulas. Structural formulas are helpful because they help you see the shape of the molecule. Okay? And any bonds between atoms are represented with lines. Okay? If you notice oxygen here, you see 2 lines. That does not mean it's an equal sign. This is a special kind of covalent bond that's called a double bond. So oxygen is actually sharing 2 sets of electrons here. Covalent bonds can also have triple bonds where they share 3 sets of electrons. So generally, covalent bonds are considered stronger than ionic bonds. Okay. Chemical formulas you mostly see either written in text or when we're writing out a chemical equation. Okay. They only show you the amount of atoms in a molecule. They do not show you anything about the shape. Okay. An important thing to note here is that the subscript tells you how many atoms there are of the thing that came before it. So in H2O, the 2 means there's 2 hydrogens. Okay, and just like in math, in exponents, when you have a 1, you don't have to write it. It's the same thing here. There's a little imaginary 1 after the oxygen that you just don't write. Alright, so that ends our notes on reviewing the structure of an atom, how to read the periodic table, and our introduction to ionic and covalent bonds. Thanks for watching!